Okay, welcome to what is just about probably the shortest subtopic in the Stage 2 physics course, and that is magnetic fields. Hopefully it's also one of the more straightforward concepts we look at, but let's get into it and make sure everyone can understand it. So as usual, let's think about what we need to know. We need to know that magnetic fields are associated with moving charges, such as charges in an electric current. Current-carrying conductors produce magnetic fields. These fields are utilised in solenoids. Magnetic field lines can be used to represent the magnetic field. The direction of the magnetic field depends on the direction of the moving charge, and that is producing the magnetic field. The direction and number of the magnetic lines per unit area represents the direction and magnitude of the electric field. Not super hard, but maybe a little confusing, but this is the key thing. This is the key skill you need to be able to do. Sketch and or interpret the magnetic field lines produced by an electric current flowing in a straight conductor, a loop, and a solenoid. And that is what we're going to focus on. So, just by way of introduction, most people are probably familiar with, when we talk about magnets, the typical sort of bar magnets. And you may, hopefully at some point, have looked at sort of iron filings and how they affect the movement of, how bar magnets affect the movement of them, and seen these sort of field lines drawn out by them. And you may also be familiar that we often talk about a north pole and a south pole on a bar magnet. And we know that opposite poles attract, so the north and the south pole will attract and pull each other together, a little bit like opposite charges attract each other. And if you try and push two like poles, whether it's two north poles like in this diagram or two south poles together, they will repel each other, a little bit like two like charges, and we see a similar sort of shape to the magnetic field as we see to the electric field for opposite charges. Just by way of convention, if you remember back to when we did electric fields, the direction of an arrow for an electric field is the direction of the force experienced by a positive charge, so it always goes away from the positive end and towards the negative end. Well, with magnetic fields, we define the direction as the direction, the north pole of a magnet points. So the north pole of a magnet will be attracted to the south pole. So if we had a little compass here, the north pole of that would point towards the south pole, or the north pole of that magnet would point towards the south pole. So in terms of what you really need to remember, when you draw magnetic field lines, they point away from the north pole and towards the south pole. So the south pole is like the negative and the north pole is like the positive when we talk about charge. Now, not only can we create magnetic fields by using permanent magnets like in up here, a magnetic field is created in the space surrounding any moving charges, e.g. electrical current flowing through wire. If you've ever pulled an electric motor apart and seen there's all these coils of wire in there, you may have even also played with an electromagnet where you've wrapped copper coil around a nail or a bolt or some other steel object and applied a charge through it, and you'll see that it becomes magnetic. So any moving charge, which is normally current flowing through a wire, will create a magnetic field in a similar manner to a bar magnet. The direction of the magnetic field is determined by the right-hand rule. The thumb points in the direction of conventional current, as you can see up here, and the thumb points in the direction of conventional current. Now, that's right. Conventional current, that should be is the direction of flow of positive charge. So positive charge would flow away from the positive and towards the negative. Two like charges would be repelled. The positive would be attracted to the negative. So you might go, why are we talking about conventional current? Because we know that current is usually electrons flowing through a wire. Electrons are negatively charged. Well, the concept of current and a movement of charge was discovered before they discovered the electron and before they knew about the structure of the atom and the electron being the particle that can move through and that being negatively charged. So they just decided to define it as the direction a positive charge would flow. So in reality, electrons flow in the opposite direction. They flow from negative to positive. So if this arrow here in the diagram is indicating conventional current, let's draw this in. Conventional current, would go up, but that would mean that the electrons are flowing in the opposite direction. So it's a little bit confusing, but yeah, hopefully it doesn't cause you too much. Once you get used to it, you've always just got to remember, are they talking about the flow of electrons? So then if they're talking about the flow of electrons, you've got to remember, well, conventional current goes in the opposite direction. Now, to work out the magnetic field, it's just these lines in red. It's just given by the curl of your fingers. So the curl of your fingers indicates the direction of the magnetic field. The number of magnetic field lines per unit area represents the magnitude of the magnetic field, i.e. the closer the lines are together, the stronger the field. So that's just like the electric field. So we need to be able to sketch what would happen in a current carrying wire. Now, generally you wouldn't be expected to draw sort of 3D representations like this because you'd be as bad at art as me. So often if it was given in an exam, that sort of simple question, you might be given like a cross-sectional. So this red here might represent the wire, and we might say that wire, we put a little cross on it. That means the wire is going down into the page. If we hang on a sec, let's do 2 of these. So that would be a wire going down into the page. If we wanted to represent a wire coming out of the page, we'd draw like the arrow head, so we'd have a circle with a dot. So that means that's out of the page. So that's out. And the cross is like the tail on a dart or an arrow. That's into the page. So if we use our right hand rule, we can see our thumb points down into the page, and in the case here for the first one, our fingers curl clockwise as we do that. So that's how we would represent the magnetic field there. If we do our right hand rule, thumb coming up out of the page, we can see our fingers now curl anti-clockwise. So that's how we would draw the magnetic field around that current carrying wire. Now, we also need to be able to do loops and solenoids, which are very, very similar. So we've got a loop here, and the current is coming up around the outside. This is, if you like, the part that would be closest to you, sort of out of the plane of the page, and then back down the back, which would be sort of behind the plane of the page, and back out through the wire. And because it's just an arrow, we assume that's conventional current. So if we think about this, we put our thumb, initially our thumb's pointing up, and that magnetic field inside that loop, in this side of that area, is curling. Our fingers are pointing in that direction. Then as we get to the back, and our thumb points back down, again, the fingers are going to be pointing in this direction here. And if we look at the scenario here at the top, well, right at the top here, this is going to be going straight into the page. It's going to be like this here, into the page. If our thumb's pointing into the page, our fingers are pointing anti-clockwise, like this example here. And then we get that, the reverse of that at the bottom. So then if we go on to a solenoid is really the same of a loop. It's just several loops. So here we have the current. Let's start over here on the right-hand side. and the current's going up at the front. So the fingers are basically pointing to the this direction. You can see that arrow, they're pointing to the left. And then if you think about it at the back here, as it comes out, well, the thumb is pointing down, and the fingers are going to, again, be pointing across to the left here. So that's going to give us that shape magnetic field. One other thing that is probably worth remembering that sometimes does come up is that if we have a solenoid, you can see almost here with the solenoid, the magnetic field is looking a little bit like the magnetic field around a permanent magnet, and a solenoid, it will act like a permanent magnet. And in this case here, this end of it would be the north pole, because if you had a compass here, all the arrows would be pointing away from that north pole, and they would be pointing, as you can see, along the top up here, they'd be pointing back down this way. Oops, wrong thing. They'd be pointing back to the, down to this end, which is the south pole of that solenoid. It's a bit confusing if you think about what's happening on the inside. Inside that solenoid, you might go, oh, everything's pointing towards the north, but shouldn't the north pole point towards the south? But we think about, when we think of this solenoid, what's happening on the outside, and you can see on the outside here that the lines are going from the north back to the south. So yeah, that is the sketching magnetic fields part. Let's just get on to the next part where we look at calculations, which is hopefully going to be very straightforward. Okay, so the next thing we need to be able to do is use basically this formula here. So the magnitude of the magnetic field strength B at a radial distance r from the centre of a current carrying conductor is given by that formula there, B equals mu naught times I divided 2 pi r, where mu on 2 pi is equal to 2 times 10 to the minus 7, and you need to solve problems with this equation. I went back looking for an exam question on this. It is pretty straightforward. I probably hardly need to do an example. Couldn't find a previous exam question on it. Obviously, the people who write the exam have decided it's too straightforward, but given there hasn't been one over the last 3 years, maybe there will be a question like that this year. So it is a good one to look at. And what we know here is that the current through the wire is equal to 4.0 amps. The radius is equal to 20 centimetres. That's not our standard unit, so we need to convert that into metres. And then we put all that into the equation. We get, oops, just lost my pen there for a sec. B is equal to 2.00 times 10 to the minus 7, that's the constant, times by the current, divided by 0.20, and we plug that all into the calculator, and we get 4.0. We're just going to have two significant figures because we had two significant figures for current and 2 there for the length, times 10 to the minus 5. And the units for magnetic strength, I didn't talk about these, but probably I should have, are Teslas. So Tesla are the units that we use for magnetic field strength. Tesla, more probably famously known now as the electric vehicle manufacturer. But maybe electric motors, magnetic fields, maybe that's the reason they are called Teslas. Okay, that's it for magnetic fields.